Okay, so now we're getting one step closer to actually doing general relativity. So what we've established so far is that in order to fully describe some space-time metric, we need this thing called the metric tensor, and that can be used to calculate all distances in the space-time I'm looking at, and I know the prescription. I know that the physical space-time distance, which I call the s squared, is just given by this prescription, right? So I have the metric tensor that tells me how to do inner products in whatever space-time I'm looking at, and then I have the coordinate vectors, and that's all there is to it, and nothing more. So let's just briefly stick to special relativity before we move on, and just remind ourselves about a few different things in special relativity. So I know, for example, in special relativity, that the metric is particularly simple. I get a minus dc squared. Notice already now I'm throwing away the c squared here, plus the x squared. So for example, I could check out the thing called a space-time diagram, which presumably you've all seen in special relativity. So let's have time propagating along this axis here, and then I have the spatial component here. Let's just stick to one dimension. So we just have motion of particles in one dimension. Now let's assume that I start, for example, at some point here in the origin at time 0. I'm sitting at coordinate location x equal to 0. Then if I'm at rest, of course, that spatial component will remain the same. I just propagate up this way. If I, for example, look at a photon that propagates with the velocity of light, velocity of light is equal to 1 in my system of units. And this, of course, I could also write as dx by dt. So very clearly you can see that the x squared and the t squared are identical, and that means that the sum here is always 0. So for a photon, I can very quickly now establish that ds is equal to 0. This is what I call a null geodesic. And there are two null geodesic in this diagram here, because I have motion only in one dimension. Normally it would be a cone in space as I propagate forwards, but here it's just two lines. So here I would have ds equal to 0, and that's photon propagation. Then you can ask yourself, of course, if I have a physical particle with mass, where would it be in this space-time diagram? Well, clearly the velocity has to be less than 1, and that means that dx is always smaller than dt, and that means that I'm always in the case where I have a negative ds squared, and I'm always in here. So that kind of curve, starting at 0, for example, and propagating this way, that describes a physical particle, that's called a time-like geodesic. And it always sits within this boundary here. Okay, so of course you can also have other types of distances in space-time. So for example, I could ask myself the question, what is the instantaneous distance to some point here which is located at this x value? So let's call that distance dx. Of course, now along this line, dt is equal to 0 because it's the distance at some specific coordinate time. Now, of course, that's a calculable quantity, but is it also a measurable quantity? And the answer, of course, is no. I cannot see this point, right? What I can see is if this point emits light and that light propagates to me, the observer sitting at rest here, it would propagate along another null geodesic, and then it would intersect with my geodesic up here, and that's where I would actually measure the light coming from this object here. Now, if space-time is static, like in normal special relativity, then I know what the physical distance to the point is here. Once I observe it, then in principle I know how far away it is, right? But in an expanding universe, things are not quite so simple, and I have to factor in the expansion of the universe, because that means the coordinate distance might remain the same up here, but the physical distance can be completely different, for example. Okay, so in any case, curves like these are called space-like. So those are the ones to do with actual distances to objects measured at some specific time, for example. And they are characterized by, okay, so remember, ds equal to 0 is null. ds squared less than 1, that's a time-like. And down here we have ds squared larger than 1, that's the space-like geodesic. So all of these, of course, exist. Not all of them correspond to physical trajectories of particles. Certainly not. Okay, all of this carries over to general relativity. It's defined normally in special relativity, but it carries over to general relativity. So one thing before we move to general relativity, let's just look at an observer at rest. So the time measured by an observer at rest, that's the one we normally call the proper time. And let's call that d tau. Again, it's infinitesimal. So that corresponds, of course, now, as I said, to an observer at rest. So if I write out the full space-time distance, it looks like this. An observer at rest would have dx equal to 0, and the time measured should be equal to the proper time. That means the total space-time distance, since there's no spatial variation, must be equivalent to the proper time over here. So what I must have here is something to do with the proper time. But notice the minus. So actually what I have here, is that ds squared is equal to minus d tau squared. And that's actually something which is quite important and very often used both in special and general relativity. That's the transformation property of this thing here. So the space-time distance, that's actually conserved under Lorentz transformations. And there's a small exercise in the notes that I put on Blackboard. If you want to actually carry out this exercise, you can show that it's true, that this is indeed conserved under even the most general Lorentz transformation you can think of. And that means this is always equal to minus d tau squared for an observer at rest. So that's an important property. So for example, just to give you an example, right, you can always calculate something in the rest frame of an observer, and then you can boost it to some other rest frame. And this thing will be conserved, but of course the coordinate distance and the time distance in the other system might be completely different from your rest frame, right? But it's important to notice this transformation property. And now we're almost at the point where we can actually start to do general relativity. So the only thing that we really need, and that's the magic of it, the only thing that I actually ever need in order to do general relativity, that is to take this thing from special relativity, what is known as the Minkowski metric. So that's this one here. I need to take that and generalize it. And that's all there is to it, basically. So if I have some crazy curved space-time, that should all be encoded in whatever metric tensor I get out. Now, of course, I have no way whatsoever of actually calculating what the metric tensor should look like yet, because in order to do that I need the field equation of general relativity, and which is the Einstein equation. I need to solve that in order to actually find the metric. But if someone gives me the metric, then I know all there is to know, because actually what happens in general relativity is that gravity acting on a particle is no longer the same as in Newtonian theory, right? Newtonian theory, you can always think of the force of gravity as some spring or a tension wire or whatever sitting between two objects and pulling. And in general relativity is completely different. The only way that gravity ever acts is through this metric. So any particle moving under the influence of gravity actually moves as a free particle. It just moves in a different space-time than the normal Minkowski space of special relativity. So it's the shape of the space-time that actually determines how a particle propagates. So if I know the metric tensor here, I know all there is to know about particle motion. And that's the first topic that we'll go through in general relativity. So we will, as the next thing, discuss what is known as the geodesic equation. So that's the equation of motion for a free particle in a more general metric than Minkowski metric.